Hi children, we are on to the last exercise of this chapter circle, exercise 10.5. So before we move on to the exercise, quickly let us go through the theorems connected to it. That is theorem 10.8. The angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. So here APB is the minor arc and it subtends an angle at the center angle AOB, and that is double the angle subtended by the arc at the remaining at a point in the remaining part of the circle. Now let us see another case when what happens when a major arc subtend an angle at the center of the circle. So here major arc is AQB. So the angle subtended by AQB at the center, it is not this AOB, it is not this angle. It will be the reflex angle AOB. It is the reflex angle AOB. So this angle will be the double of the angle subtended by this arc at a point in the remaining part of the circle. So this reflex angle AOB is double the angle APB, or angle APB is half of the reflex angle AOB. Now what will be when it is a semicircle? So here APB and AQB both are semicircle. So what will be the angle subtended by any of them at the center? It's a straight line, 180 degree. So the angle subtended at any other point on the remaining part, it is 90 degree. That is angle of semicircle. It is right angle. It is right angle. So keep now next theorem. Angles in the same segment of a circle are equal. So that is here in the first figure, angle AQB is the angle subtended by this arc APB at Q. Now it will be same as angle ARB. Now if you take any point here, all will be same. AQB equal to ARB. Next theorem, the sum of either pair of opposite angles of a cyclic quadrilateral is 180 degrees. So here it is very clear. Now this forms a cyclic quadrilateral. So the sum of the opposite angles, it is 180. And if the sum of the pair of opposite angles of a quadrilateral is 180, then the quadrilateral is cyclic. So what do you mean by cyclic quadrilateral? Cyclic quadrilateral where all the four vertices of the quadrilateral lie on the circle. Okay children, now let us move on to the first question of exercise. Now question number 1. In the figure, A, B and C are 3 points on a circle with center O such that angle BOC is 30 degree and angle AOB is 60 degree. D is a point on the circle other than the arc ABC. Find ADC. So we need to find angle ADC. So what will be angle AOC? AOC is the angle subtended by this arc ABC at the center. So angle AOC is equal to angle AOB plus angle BOC. That means 60 plus 30, 90. So this angle subtended at the center is 90. So as per the theorem, what will be angle ADC? The angle subtended by the same arc on any other point on the circle. So what it will be? Half of AOC. Angle ADC will be half of angle AOC. So it is equal to half of 90. So that is 45 degree. Now next question. A chord of a circle is equal to the radius of the circle. The chord and the radius are equal. Find the angle subtended by the chord at a point on the minor arc and also at a point on the major arc. So let us see one circle, and what we need? A chord that is equal to the radius of the circle. So one chord AB and radius. That means OA is equal to AB. So let AB be the chord equal to the radius OA. Now what we have to find? Angle subtended by the chord at a point on the minor arc, on the minor arc and at a point on the major arc. So that means we need to find APB and AQB. That is what we have to find. So here AOB is the angle subtended by the chord at the center. And just look into this triangle AOB. Here OA is the radius, OB is again radius, and AB is the chord equal to the radius of the circle. That means this is an equilateral triangle, is it? Now we have to find APB. Now APB is the angle subtended by the chord at a point P on the major arc. So AOB is an equilateral triangle. And what is the angle? Each angle of an equilateral triangle? Yes, it is 60. All the angles of an equilateral triangle is 60. So angle AOB is 60. When angle AOB is 60, then what will be angle APB? It will be half of angle AOB. Then APB is equal to half of 60, that is equal to 30. Now next we have to find angle subtended at a point on the minor arc, that is angle AQB. So to find the angle AQB, we need to find the reflex angle, that means the angle subtended by this major arc APB at the center, that is the reflex angle we need to find. So AOB is 60. So what will be its reflex angle? It will be 300. 360 minus 60. So it is 300. So what will be angle AQB? It will be half of reflex angle AOB, is it? So it will be half of 300, that's equal to 150. Got it? Now let us move on to question number 3. In figure, so let us see the figure first. Yes. Angle PQR is 100, where P, Q and R are points on the circle with center O. Find angle OPR. So PR is a chord in the minor segment because it is above the center. It is above the center. So PR is a chord in the minor segment of the circle. And PQR is the angle subtended by the major arc PR. PR at Q. PR at Q. That is 100. So what is the angle subtended by this major arc PR at the center? That will be double of this PQR. So double of 100. So it is equal to 200. Now, when we get 200, we can find the other angle. That is angle POR that we can find. That will be 360 minus 200. That's equal to 160. Now, what we have to find? We have to find angle OPR. That is what we have to find. So here, PQR is an isosceles triangle. Why? Because OP and OR are the radii of this circle. So when these two sides are equal, the base angles are also equal. That means angle OPR equal to angle ORP. Now, with the angle sum property, these three angles, sum of these three angles is 180. So, angle OPR plus ORP is equal to 180 minus 160 equal to 20. So, each angle will be 10. So, that means angle OPR is equal to 10. Now, let us move on to question number 4. Again, figure, yes. Angle ABC is 69, ACB 31. Find angle BDC. So, to find angle BDC. Okay. Now, let us take the triangle ABC. In that, angle B or angle ABC, that is 69, and angle C, which is equal to 31. So, we can find angle A using angle sum property. So, it is 180 minus 69 plus 31, that is equal to 80. So, we got angle A. Now, what is the connection between angle BAC and BDC? Angles at the same segment. Angles in the same segment. Both are from the chord BC. Same segment. So they are equal. That means angle BDC also 80 degree. Is it clear? It's very, very simple one. Okay, children, now let us move on to next question. Question 5. So figure, yes. A, B, C and D are 4 points on a circle. Okay, A, B, C, D, 4 points on the circle. A, C and BD intersect at E such that angle BEC is 130 degree and ECD is 20 degree. Find angle BAC. So to find angle BAC. Now look into the figure carefully. This angle BAC and BDC are the angles in the same segment, is it? So they are equal. So to find this, if you find BDC, that is enough, is it? Because here we know one more angle here. So let us try to find angle BDC. So to find that, to get BDC, we know this is 20. So if we get this angle, that is angle ECD, easily we can find D. So how we will find angle CED? That angle and this 130, what is the connection between them? They are linear pair, is it? They are linear pair. These two angles are linear pair. So angle CED is equal to 50. Now we can find angle D using angle sum property. So that is 110. So that means angle BAC also 110. Got it? Shall we move on to the next question? Okay then. Let us move. Question 6. ABCD is a cyclic quadrilateral whose diagonals intersect at a point E. So first let us draw the figure according to this. ABCD is a cyclic quadrilateral. So let us first draw a cyclic quadrilateral ABCD whose diagonals intersect at a point E. Okay. Now, if angle DBC is 70, angle DBC is 70, then angle BAC is 30. BAC, that is 30. Okay. Find angle BCD. You have to find angle BCD. So let us see how to get it. Yes, angle DBC and angle DAC are angles on same segment. So this angle also 70. Yes. Now, angle A plus angle C is equal to 180 because opposite angles of a cyclic quadrilateral is supplementary. So A is 30 plus 70, 100. So what will be angle C? 180 minus 100, that is equal to 80. So we got angle BCD, we got. Now one more question is given. Further, if AB is equal to BC, find ECD. So suppose AB equal to BC. AB equal to BC. Then when AB is equal to BC, then this triangle ABC will become isosceles triangle. And we know that in an isosceles triangle, the base angles are same. So when this is 30 degree, then BCA also will be 30 degree. Is it? So that will be 30 degree. So what we have to find? We need to find ECD, this remaining part. So the total is 80, this much is 30. So what will be ECD? It's so easy. So it will be 50. Is it? Understood? Okay, now let us move on to question number 7. If diagonals of a cyclic quadrilateral are diameters of the circle through the vertices of the quadrilateral, prove that it is a rectangle. Okay, so a circle and the diagonals of this quadrilateral pass through the center. What we have to prove? It is a rectangle. It is a rectangle. It's very, very simple. So let us see how to prove it. Here, OA, OB, OC, OD are all radii of the circle. They are all equal. So when they are all equal, AC and BD also equal. Otherwise also it is equal because they are the diameters of the circle. No, so they are equal. So when the diagonals of a quadrilateral are equal, then we can call it a rectangle. Now, another way also we can prove this. Another proof. That is, angle A equal to angle C equal to 90. Why? Because angle subtended by the diameter BD, that is a semicircle. So they are 90. Similarly, angle B is equal to angle D is equal to 90 because they are the angles subtended by the diameter AC. So all the four angles become 90 degree. So it is a rectangle. That's it. Clear? Got it? Very, very simple. Now let us move on to question number 8. If the non-parallel sides of a trapezium are equal, prove that it is cyclic. Okay, so a trapezium ABCD, and it is given that the non-parallel sides are equal. So AB and CD are the parallel side, and it is given AD and BC are equal. We have to prove that it is cyclic. That means we need to prove the opposite angles are supplementary. Sum of the opposite angle is 180 degrees. That's what we have to prove. So ABCD is a trapezium. AB parallel CD and AD equal to BC. To prove ABCD is cyclic, now draw AM and BN perpendicular to BC. Now we got two triangles here on either sides. Now in triangle AMD and triangle BNC, AD equal to BC. It's given. And AMD equal to BNC equal to 90 degree. Yes, by our construction. And AM equal to BN. Distance between parallel lines are equal. So these two triangles are congruent by RHS congruence. Okay. So we can prove, we can say angle ADM is equal to angle BCN. Corresponding part of congruent triangles. That means angle D equal to angle C. Equation 1. Now it is a trapezium. This AB and CD are parallel. So I can say angle A plus angle D is equal to 180. Why? Interior angles on the same side of the transversal. AB parallel CD and AD is the transversal. So A plus D equal to 180. But D is equal to C here. So instead of D I can write A plus C equal to 180. That means A plus C, A and C, opposite angles. Opposite angles of the trapezium are supplementary. So, ABCD is cyclic. Is it? Now, move on to question number 9. Two circles intersect at 2 points B and C. Don't get complicated with the figure. Figure little bit complicated, but observe properly and don't get scared of the so much lines and are there. It's very simple. Okay. Two circles intersect at 2 points B and C. Through B, two line segments ABD and PBQ are drawn to intersect the circles at A and D. Intersect the circle at A, D and P. A, D and P, Q respectively. Okay. Prove that angle ACP is equal to angle QCD. So first you observe the figure carefully. Concentrate and observe what all things you can see in that figure. What all theorems you learned are coming. Just concentrate on the figure and think about it. So these two angles are equal. That is what we need to prove. Now, let us join the chord AB and DQ. Now see the magic. See, angle ACP, now you will say easily, which is the same angle, same segment, angle on the same segment. Yes, angle ABP. They are angles on the same segment, so they are equal. Now, come to the chord DQ. There also you can see, no? Yes, angle QCD and QBD. They are also equal. Is it? So, now, look at these two angles. Angle ABP and QBD. These two angles looking each other. They are equal. Why? Vertically opposite angles. Now you look into these three statements carefully. See, ACP equal to ABP. Here, ABP equal to QBD. Here, QBD equal to QCD. All are equal. That means ACP equal to QCD. So from 1, 2 and 3, we proved that angle ACP equal to angle QCD. Very simple, is it? Now, next question, 10th one. If circles are drawn taking two sides of a triangle as diameters, prove that the point of intersection of these circles lie on the third side. So you have to read the question or understand clearly. Two circles are drawn taking two sides of the triangles or diameter. So first let us draw a triangle. And let us draw two circles, one with AB as diameter and one with AC as diameter. So two circles drawn. So they are meeting at the point D. Here what we have to prove? This point of intersection, that is this D, lie on the third side, but by the figure it is lying on the third side. We see very clear, is it? Very clear, but we need to prove it. We need to prove it. Though it is very clear in this figure, we have to prove it. So how we will prove that? So let us see. Join AD. So AD is the common chord, is it? Is the chord in the both the circles. Okay. Now ADB. ADB is the angle subtended by diameter AB at D, is it? And we know that the angle subtended by the diameter at any point is what? How much? 90 degree, no? Yes. Now similarly, ADC, that is the angle subtended by at D by the other diameter AC, that also 90 degree. So these two angles are 90 degree. So when we add them, what we get? We get 180. That is, angle BDC is 180. That means it's a straight angle. That means BC is a straight line and DC point on it. So D lies on BC. Very, very simple. Now moving on to question 11. ABC and ADC are two right triangles with common hypotenuse AC. Prove that angle CAD equal to CBD. So let us first draw two right triangles. Okay, two right triangles are there, and what we have to prove? Yes, angle CAD is equal to angle CBD. This is what we have to prove. Now these points, this angle ABC right angle at B and angle ADC right angle at D. Okay. AC is the common hypotenuse. And it is given that it's a right angle. That means angle AB and angle D are 90 degree. So, therefore, they lie on the semicircle. Because angle at any point of the circle becomes 90 degree means they lie on the semicircle. That means AC is the diameter. Therefore, A, B, C, D, the points are concyclic. So, CD is a chord. CD is a chord. Now, see, CAD and CBD are angles on the same segment. Is it? So, they are equal. Question number 12. The last question of this exercise. Prove that a cyclic parallelogram is a rectangle. So let us draw a circle, a cyclic parallelogram ABCD. We need to prove ABCD is a rectangle. Given that ABCD is a cyclic parallelogram and angle A plus angle C is 180 because opposite angles of a cyclic quadrilateral. So sum of A and C is 180. But angle A equal to angle C, why? Because it is a parallelogram. Opposite angles are equal in a parallelogram. Therefore, angle A plus angle A equal to 180. So angle A 90, angle C 90. Similarly, angle B 90, angle D 90. So all the angles are 90. Therefore, it is ABCD is a rectangle. So that is the end of this exercise and this chapter. Go through it, study well. All the best, children. Thank you.